a high-quality knowledge podcast for hitchhikers traveling the galaxy. This is Lab 42.
Welcome back to the Deep Dive. Today, we are going to look at something that I think we all sort of take for granted. We're talking about logistics.
But not your typical kind of logistics.
No, not the kind where you order a toothbrush and it shows up 2 days later. We are talking about the highest stakes logistics imaginable.
That's right. We are looking at a system where a delay doesn't just mean a refund or, a bad review.
Yeah.
It means the difference between life and death. We're diving into the fascinating high-speed world of organ transplant logistics.
And honestly, when I started reading through the research for this, I thought it was going to be about surgery, scalpels, doctors, all the medical drama stuff.
Right.
But the source material we have today, it frames it completely differently. It frames it as a battle against physics.
It really is. It's a collision of thermodynamics, fluid dynamics, and this field called cybernetics.
Yeah.
It's about fighting the fundamental laws of the universe.
Okay, let's unpack this, because the research starts with a pretty heavy hitter. It opens with Erwin Schrödinger.
The cat guy.
Yes, the cat guy. But apparently back in 1944, he wrote this book, What is Life? And he gave a definition of life that just sets the stage for everything we're about to talk about.
He did, and it's such a profound insight. Schrödinger defined life as something that resists entropy.
And entropy is, it's just disorder, right? Chaos.
Exactly, yeah. It's basically the second law of thermodynamics. It tells us that the universe just naturally moves toward disorder. A hot cup of coffee cools down.
A building crumbles into dust.
Living bodies decay. The arrow of time always points toward chaos and, well, death.
So Schrödinger said life is the act of fighting that, just constantly pushing back.
He put it beautifully. He said life survives by consuming negative entropy. We eat, we breathe, we take in energy to maintain our internal order against this constant push from the universe.
And this is where the logistics part comes in. The source draws this really stark contrast between what it calls dead cargo and living cargo.
Right. Think about Amazon or, any delivery service. When they move a box of bottled water or a new TV, that cargo is effectively dead.
It's stable.
It's at thermodynamic equilibrium.
Mm-hmm.
If it sits in a warehouse for an extra week, it's fine. A delay costs money, sure, but the TV doesn't, physically cease to exist because the truck got a flat tire.
But an organ is living cargo.
Precisely. From the moment an organ is removed from a donor, it is on a countdown. It's cut off from its energy source, so it starts consuming its own reserves. It immediately starts sliding down that slope toward entropy.
So the thesis here, the big idea, is that organ transplant logistics isn't just about moving an object from point A to point B.
Not at all.
It's a time control technology.
It's an anti-entropy struggle. The whole goal is to grab the arrow of time and forcibly physically hold it back.
I love that image. So let's get into the nitty-gritty of how they actually do that. This leads us to our first big topic, thermodynamics, or as our notes call it, the time machine in the icebox.
It's a fitting title, because once that organ is out, you are dealing with something called ischemic time.
Okay, what's that?
That's the time the organ spends without any blood flow. And the limits are, well, they're terrifyingly short.
I saw the data points here. For a heart, it's something like 4 hours. A liver gets maybe 12. A kidney, 24.
And that's not a lot of time.
No.
And that's not a suggestion. I mean, that is the physical limit before the organ runs out of ATP, the energy currency of the cell.
Mm.
Without oxygen, the cells, they switch to anaerobic metabolism.
Which is bad.
Very bad in the long run. It causes a buildup of lactic acid. The cells become acidic, a state called acidosis. If that goes on too long, the cell membranes just fail.
Okay.
And even worse, if you try to reconnect that organ to a blood supply later, you get something called reperfusion injury. Basically, the organ is so damaged it can't handle the rush of oxygen and it fails.
So the logistics team has to stop that biological clock, and their weapon of choice is temperature.
Specifically, something called the Q10 effect.
Okay, explain the Q10 effect to me.
It's a biological rule of thumb, really. For every 10 degrees Celsius drop in temperature, the metabolic rate of a biological system slows down by 2 to 3 times. So the goal is to get that organ down to 4 degrees Celsius and to do it rapidly.
4 degrees? Why 4? Why that specific number?
Because at 4 degrees Celsius, the organ's metabolic rate drops to about 10 to 15% of normal. It induces a state of, suspended animation. It's like hibernation.
So it stops burning through its fuel.
It just sips it.
But here's the question that popped into my head, and I'm sure a lot of people are wondering too. If cold is good, why not just freeze it? Why not 0 degrees or, even lower?
It's such a crucial distinction. We want cooling, not freezing. The moment you hit 0 degrees, you trigger a phase transition.
Water turns to ice.
And when water freezes, it expands and it forms these incredibly sharp crystals.
Which would just shred the cells, turn them into mush.
Precisely. Those ice crystals would puncture every cell membrane, so you have to hit this Goldilocks zone.
Cold enough to stop entropy, but warm enough to prevent physical destruction.
Exactly.
And it's not just ice in that cooler box, right? The source mentions these special solutions, UW solution, HTK solution.
Right. Those are preservation fluids. They're like a chemical fortress for the cells. They act as buffers. They stop the cells from swelling up, and they neutralize all those toxic byproducts we mentioned.
Okay, here's where it gets really interesting for me. The source compares this cooler box to a time machine using Einstein's relativity.
It's a beautiful analogy, isn't it? In relativity, if you travel near the speed of light, time slows down for you relative to everyone back on Earth.
That's time dilation, right?
The cooler box creates biological time dilation. For every 1 hour that passes in the physical world, in the ambulance, in the helicopter, the organ inside that box only ages about 6 minutes biologically.
That is mind-blowing. It really is. The box literally separates the organ from the flow of time outside.
It does. So when we say logistics is just moving stuff, it's so inadequate here. This system is a technology that stretches the present moment, just for a little while, into the future.
Okay, so we've slowed down time inside the box. That part I get. But you still have to move the box across physical space. And this is where we run into the next big enemy, friction.
Or, as a physicist would call it, fluid dynamics.
This part of the research compares city traffic to a fluid, and I think anyone who has been stuck in rush hour knows exactly what that feels like.
Oh yeah, it's a high-viscosity fluid, like honey or sludge. The source even uses the concept of the Reynolds number. In fluid dynamics, a high Reynolds number means the flow is chaotic and turbulent.
That's rush hour.
That is rush hour. Cars are just particles in this thick, turbulent mess. A regular truck gets stuck in that swamp. But in Oregon, it just can't afford that.
So how do they beat the friction?
They have 3 main solutions, and each one is basically a physics hack.
All right, let's start with solution A, the helicopter.
The helicopter represents what you'd call a phase shift. If the road is a 2D plane with all this friction, the helicopter shifts the movement into 3D space.
It literally just rises above the problem.
Exactly. It leaves the boundary layer of the Earth where all the friction is. And in this scenario, the air traffic controllers, they play the role of Maxwell's demon.
Maxwell's demon. I feel like I should know that.
It's a thought experiment in physics. Imagine a tiny demon controlling a door between 2 chambers of gas, only letting the fast molecules through.
I see.
The air traffic controllers do that. They clear the airspace. They create a vacuum tube, an empty corridor in the sky, specifically for that helicopter. It's not moving through traffic. It's moving through a space where traffic has been made not to exist.
But helicopters can't always fly. Weather happens, fog, storms, you name it. So sometimes you have to use the road. That brings us to solution B, the ambulance.
And the source compares the ambulance to a superconductor.
Okay, I love this analogy.
It's my favorite one, the whole thing. A superconductor is a material that conducts electricity with 0 resistance. It does this by expelling magnetic fields from its interior. It's called the Meissner Effect.
So the ambulance is the superconductor.
Yes, and the siren and the lights, that's its repulsive field.
Wow. It pushes the magnetic field of the other cars away.
It creates what the source calls the Moses effect. You see it happen. The cars stick to the sides of the road, the wall effect, and it leaves the center completely empty.
It creates a clear path.
In fluid dynamics terms, it turns that turbulent, chaotic flow into laminar flow. Smooth, streamlined, basically resistance-free movement right down the middle.
It's incredible, but there's a third solution, right, for when you're in a smart city. Solution C, the smart signal.
This is where we get into something called constructive interference. It uses V2X, communication vehicle to everything.
So the ambulance is talking to the traffic light.
Exactly. It's sending its speed and location to the city grid. And the city then manipulates the lights to create a green wave.
So the lights turn green just before the ambulance even gets there.
Right. From a physics perspective, this is constructive interference for the ambulance. It amplifies its movement forward. And at the same time, it creates destructive interference for all the cross traffic.
Lights for everyone else.
Exactly. It stops that stop-and-go driving, which wastes so much energy and time. The ambulance just maintains its inertia. The city is literally reshaping itself to pull the ambulance forward.
This is amazing. So we've got thermodynamics, slowing down time, fluid dynamics, parting the sea of traffic, but someone has to coordinate all of this.
The human in the middle of it all.
And that brings us to our final segment, cybernetics, the human algorithm.
Right. We're talking about the transplant coordinator. Now, I used to think of these people as just admins, making phone calls, checking clipboards.
Me too.
But the source calls them system controllers. They are the brain of the whole operation, and it uses a very specific biological metaphor for them, the synapse.
A synapse is the gap between nerve cells, right?
Right. It is. It's where an electrical signal gets converted into a chemical one to bridge that gap. The coordinator is a transducer. They bridge the gap between totally different languages.
What do you mean by languages?
Well, you have the language of medicine, vital signs, blood types, medical urgency. Then you have the language of law consent forms, procedures, and finally the language of logistics, weather patterns, traffic density, flight times.
And those systems don't talk to each other. A surgeon isn't necessarily checking the weather radar.
Not at all. So the coordinator is the one who translates patient's blood pressure is dropping into the helicopter needs to launch in exactly 10 minutes. They convert a medical signal into a logistical one.
And they use two types of control, right? Feedback and feed forward.
This is classic control theory. Feedback control is reactive. The helicopter can't fly because of a storm. Okay, switch to the fast train or another ambulance. You detect an error and you correct it.
That's just standard problem solving.
It is. But the mark of a real pro is feed-forward control. That's predicting the error before it even happens.
So like seeing the weather forecast and moving the surgery time up?
Precisely. You see a storm front approaching on the radar, so you call the surgeon. You say, look, we need to extract that organ an hour early to beat the rain.
Yeah.
You are adjusting the system based on a prediction of a future problem. That's next level.
This raises a really important question, though. If it's all about calculations and predictions, why not just use AI for this? Why do we still need a human in the loop?
Because of heuristics and because of the nature of the data involved. AI is brilliant at optimizing for efficiency, but so much of this work deals with unstructured, deeply emotional data.
Give me an example.
Okay. Imagine a donor family. They've just lost a loved one. They are grieving, and they ask for 5 more minutes to say goodbye before the surgery starts.
An AI might look at that and just say, inefficient, denied.
Exactly. An AI optimizes for time. But a human coordinator understands the unstructured data of grief. They know that giving that family those 5 minutes is crucial for the ethical stability of the whole system. They find a way to adjust the logistics to accommodate that very human need.
They act as the homeostasis of the system, keeping it stable, not just mechanically, but ethically.
They balance the cold, hard logic of survival with the warmth of human empathy. And that's something an algorithm just can't do yet.
So let's zoom out. We've looked at the science, the tech, the human element. What does this all mean in the end?
It brings us back to that final equation. In nature, the equation is simple. Death equals end. Entropy always wins. But this entire system, the cooling, the speeding ambulances, the coordinators, it changes the equation.
It changes it to death equals new life.
Yes. We are using 3 different branches of science thermodynamics to slow time, fluid dynamics to remove friction, and cybernetics to control the complexity, all to reverse the arrow of time, just for a moment.
It really forces you to rethink what logistics even is. We usually think of it as kind of boring, moving boxes. But in this context, logistics is the only thing standing between the inevitable laws of the universe and the miracle of extending a life.
It's the highest form of resistance. It's humanity looking right at the second law of thermodynamics and saying, not today.
And here's the thought I really want to leave you with. The source mentioned that an organ has the shortest expiration date of any product on Earth. Just a few hours, that's it.
But if it's delivered successfully, it leaves the longest lasting impact.
Decades of life. It's a powerful reminder that we are all part of this potential life support machine. Every time you pull your car over for an ambulance, you aren't just following a traffic rule. You are participating in a fluid dynamics equation to lower resistance. You are helping to deliver a miracle.
You're part of the anti-entropy struggle.
Exactly. Thank you for joining us on this deep dive into the science of saving lives. It certainly changed the way I look at an ambulance racing down the street.
Me too. Absolutely.
We'll see you on the next deep dive. Stay curious.
That's all for today's episode of Lab 42. If you enjoyed this story of impossible engineering, leave us a review. Safe travels, hitchhikers. See you in the next galaxy.